So I'm trying. Okay. So yeah, I remember last time I gave a Zoom talk at KS. That was I think around 5 years ago, and I was talking about mini-mood anomaly. And now many things have changed, and not that many people are working anymore on mini-mood anomaly. But of course, there are some other anomalies that just keep emerging. So you may have heard of this very high energy neutrino event recorded by KM3NeT collaboration. If you have not, I have a very long intro to that, and that's basically the topic of this talk here. But before talking about that event, I'd actually like to talk about IceCube, because IceCube has been the main player in this game of high energy neutrinos for more than a decade. So as you may know, the IceCube is a neutrino telescope located at the South Pole. Here's their station on the left, in the left panel, and in the right you can see their instrumented volume. So they basically drilled a lot of holes at the surface, and they inserted a bunch of strings, and strings are carrying a bunch of photomultipliers, which are stored in football, or should I say soccer shape digital optical moduli. And what you always see in these kind of plots is a comparison of the detector to the size of the Eiffel Tower. So you need 3 Eiffel Towers stacked on top of each other to match the height of IceCube, and that basically implies that it's kilometer in height, but it's also it's a cube, so it's kilometer cube detector. So what IceCube has, and by the way, I haven't mentioned, but yeah, feel free to interrupt me with any question during the talk. What I want to say in the next few slides, I just want to set the stage on what IceCube has been doing, and then I'm going to introduce the puzzle that has emerged now when KM3NeT detected their event. So here, IceCube has basically pioneered this high energy neutrino astrophysics. The top plot here on the y-axis, you got the fluxes. On the x-axis is the energies. So if you think about all the neutrinos above, say, 100 TeV, they are stored from all possible sources that have been detected. They're given here for different flavors in red data, and also this gray region. And this basically, this is the so-called diffuse neutrino fluxes, basically taking into account all the detected neutrinos, no matter what is the source. For most of these neutrinos, we don't know the source. What IceCube has, however, managed to determine is the actual source for some of these neutrinos. For instance, you may remember this TXS, Texas source from 2017. That was Blazar, and they detected a couple of PeV neutrinos from there. Here on the bottom plot is just the graphical, artist's view of Blazar, where you have a supermassive black hole in some galaxy, and then you have matter, which is then accretes on that, and this process allows for a very efficient production of neutrinos. And in this case, the neutrinos are in this jet streaming toward the Earth. That was at the Blazar TXS 0506, but more recently they also identified this NGC galaxy, sources from neutrinos from the NGC galaxy, which is also an active galaxy. And here the neutrino energies were between 10 to the 3, 10 to the 4, so above TeV, and not reaching the PeV. And in addition to those two, I believe there is also another Blazar, which has a pretty high significance. So these sources of high energy neutrinos are kind of stacking up, but we still don't have the explanation for all of the neutrinos ever detected. But this is still a great step forward. All of these things is discussing like extragalactic neutrino sources. I should also point out that the IceCube has detected neutrinos from the galactic plane. So that's shown here in the lower right plot. We can look toward the galactic center in optical. That's this first stripe here. We can do that in gamma rays. That would be the second stripe. and these last three ones are actually connected to IceCube's publication in 2023, where they managed to detect more than several neutrinos from the galactic plane. So now we can also look at toward the galactic center using neutrinos, not only photons. So this is about the detection and the various events that IceCube contributed, but what is more important for my talk actually is the energetics of the events. So here I want to point out on this
Hi.
slide. Yeah.
So I have a question. So can you go back to, yeah. So far there are no, let's say, observation of GeV scale neutrino, right, from IceCube or no?
Oh, they do have a bunch of GeV neutrino events, but I'm not, so this would be atmospheric neutrinos, right? And
Yeah.
they do, but in this plot, I'm basically focused on high energy neutrinos. So this plot goes from 10 to the 3 GeV. Yeah, somehow I didn't include that. That's also something that they're actually very good at. And that would
Okay.
be using the IceCube in the center has this, well, should I call it subdetector? It's just a more finely spaced strings, which is called the deep core, and they detected a bunch of atmospheric neutrinos, and using that, they can constrain the atmospheric mixing angle theta 2-3. And actually, it's a pity that I didn't include anything about that because they are competitive to dedicated experiments such as T2K and NOVA. So that's something really good they're doing at low energy. But this talk is more about, as you know, see from the title, about very high energy. So I kind of didn't include that in the discussion. But
Yeah.
definitely, there is atmospheric neutrinos, a bunch of atmospheric neutrinos being detected by IceCube.
Yeah. And one more question. So whether is it possible for them to distinguish between let's say atmospheric neutrinos and neutrinos which are coming from, let's say, very far away, but let's say I'm talking about GeV scale neutrinos.
GeV neutrinos, in principle, not. But you know, if you have something low energy and the GeV coming from very far away, that would be very strongly suppressed in flux.
Okay. You mean they will be
Because you know, atmospheric neutrinos are still produced relatively close, so I would assume that they would be much stronger. I'm I'm actually maybe not that much familiar with dedicated GeV, like you know, supernova flux would die at 10 MeV. Then you start seeing atmospherics here. In principle, you could have sources, but you know, when we talk about far away extragalactic sources, we typically focus on these high energies above the atmospherics, something that we cannot produce at Earth nor in the atmosphere.
okay, okay, thanks.
So yeah, this is a lot about IceCube, and let me just spend one more slide on IceCube. And now I just want to introduce a glacial resonance process. So as I said, IceCube detected a bunch of high energy neutrinos, more than hundreds of neutrinos above, say, 50 TeV scale. And one of them is sort of special, and that corresponds to the electron antineutrino, which scatters on the electron and produces an on-shell W boson. And why is that interesting? Well, if you think about the cross section, you know the propagator suppression 1 over p squared minus m squared. And so you have a resonant enhancement when p squared equal m squared, and p squared in this case is the Mandelstam S. So the Mandelstam S would be the neutrino energy multiplied by 2, multiplied by the electron energy, which is the scatterer. And if this is equal to the W boson mass, you have this resonant enhancement in the cross section. We know the W boson mass, we know the electron mass, so we can compute the neutrino energy, which is required to induce such a process. And it turns out to be around 6.3 PeV. And then indeed, IceCube, if some process has a large cross section, then you know, if fluxes are reasonable, you could have these kind of events detected. And indeed, IceCube back in 2021 detected one shower with an energy of 6.05 plus minus 0.72 PeV. So that prediction definitely fits the energetics of the glacial resonance. And they also made a bunch of complementary studies in order to infer that it's indeed corresponding to a glacial process. For instance, this W boson is going to decay. In most of the cases, of course, it decays hadronically. So there will be some pions producing muons, and this is, for instance, what they call a leading muon in their detector, which they managed to identify and record all this light collected by the photomultipliers. It's not that important for my talk. For my talk is important the energy here, 6 PeV, but I can also point out that this is an interesting process because antineutrinos can induce this process, neutrinos cannot. So that's a way how to distinguish neutrinos from antineutrinos at high energy, because IceCube doesn't have a magnet inside ice that would just steer electrons to the left, positrons to the right, or something like that. So this is a very interesting way also to probe the flavor. But the take-home message from this slide is just the energy of this recorded event. That's the highest energy event in the IceCube's data set, and it's at around 6.3 PeV. So much about IceCube. I said a lot of stuff about IceCube, but the talk is actually not about IceCube. The talk is about this new neutrino event by KM3NeT. KM3NeT is, as one of my collaborators calls it, it's a melted version of IceCube. So instead of ice, you use water as your detection material, and you basically perform the same strategy what they did in the South Pole now in water. And this is actually done in Europe. They have two sites. One is around somewhere in France. And actually, that's the location where they collect low energy neutrinos, atmospheric neutrinos. So just in connection to the previous question, KM3NeT has also detected a bunch of atmospheric neutrinos at low energies. At the other site where they collect very high energy neutrinos is very close to the coast of Sicily, and there they performed this kind of work. So you see it's similar but somewhat different than what is done in the South Pole. You basically have this again soccer size, more, even larger than soccer size DOMs, which are storing a bunch of photomultipliers, and they're being deposited in water. And this is how it looks. This is some artist view of that detector in water, where you can see that all these strings are actually attached to the bottom of the sea, and that would be a Mediterranean Sea at the south of Italy. Some of you may have also remembered the successor of KM3NeT experiment, and that would be Antares experiment, which was also operating in the Mediterranean. So this experiment has already been taking data for a couple of years, and what this talk is actually about is about this a very high energy event, which is called KM3 230213. So this number should be read in a flipped way. So this they detected an interesting event on 13th of February 2023, so more than 2 years ago. But they published this year because it took a lot of time to to verify that event. What this event is all about is that they detected a roughly 120 PeV muon propagating in the detector, giving a muon track. It is assumed to be coming from a neutrino with a median neutrino energy of 220 PeV. You see, when you have a muon, that muon can be produced somewhere here in the detector from the neutrino charge current. So neutrino upscattering to muon through the exchange of W boson. But it can also happen somewhere en route to the detector, somewhere outside of the detector. And right now, the collaboration still doesn't know where the interaction has happened. So that's why they actually give a distribution on the neutrino energies, because if interaction happened outside of the detector, muon would be actually be losing energy until reaching the detector, and that means that would also shift the estimate on the original neutrino energy. So the median neutrino energy is 220 PeV, and that is actually on the lower side, because if you look at the density distribution for that energy for the energy of that event, you can even see a non-zero PDF for that to be exceeding like EEV. For my talk and in our work that I'll present, I will basically be working with these median values of energies and directions of neutrino event reported. So what is interesting here, let's look at this 220 PeV and let's compare that to the glacial resonance event from IceCube. So that would be 220 PeV versus 6 PeV, more than factor of 10. Meaning that we have as the title of this slide says, we have a new energy champion, and that's actually by a lot, right? So now we have a neutrino event at more than 50 times bigger energy than the glacial resonant event. And that is actually surprising, because think about IceCube operating for more than 15 years, almost 20 years, and IceCube still has a larger volume than KM3NeT. KM3NeT has not yet reached their goal of kilometer cube, which means that if IceCube has a larger volume and has been taking data for a much longer time, why is it that KM3NeT shows up and sees such a high energy event, and IceCube in all these years has not seen anything above 6 PeV? So that's really surprising, and that's actually an anomaly which can be quantified. And that was done in this paper by Shirley Lee, Pedro Machado, and their collaborators, where they quantified the fact that IceCube has not seen neutrinos of this order 100 PeV energy as with a statistical significance of 2 to 3.5 sigma. And this number varies depending on what is your assumed neutrino source. So let me just quickly summarize their works. First, they assume that the origin of this this high energy neutrino would just be part of the diffuse flux, so which is commonly parameterized with normalization and the spectral index. Spectral index just tells you how fast your flux drops with energy. So here we have a lot of data from IceCube, and the combined fit with these true-going muons and some other data sets like high energy starting events would give you this red region here. And the result for the KM3NeT is given here in green. So if you just start, moving this red region and approach to the green one, you will find that you need like 3 shifts, roughly 3 sigma tension between these two. So that's for the case of parallel diffuse. The bottom plot here is for the cosmogenics. That would be assuming that this neutrino is actually coming from high energy cosmic rays, high energy proton being a cosmic ray, interaction with the cosmic neutrino, cosmic CMB, so cosmic um, microwave background, and that would produce a delta resonance, which can then decay into neutrinos, among other things. And in this case, you can also see that IceCube set a limit at the 90% confidence level, and this data point of KM3NeT is sitting here in the forbidden region with this uncertainty, which if you start, extending, you again find roughly a 3 sigma tension. So in these cases, for both of these sources, you suffer from the volume and the time data taking time, because IceCube has taken data for a much longer time. The time factor can be alleviated, which removes the tension from 3 point something to order 2 sigma. If you assume that your high energy neutrino is coming from some transient source, it's basically as a single source which has been active, for instance, think about seconds, minutes, or days. So if that happens during the operation of time of KM3NeT, that would mean that for detecting that particular event, it doesn't matter that IceCube has been active for those extra 20 years because that particular source was not active during those times. Actually, that's going to be the system that I'll be working with when explaining this anomaly with BSM, because that will only depend, our explanation will only depend on a particular direction and in turn one source. But to introduce that, I just need one or two more slides. So here I'm just illustrating this tension. And I should also point out that the collaboration itself, the KM3NeT collaboration, when they announced this event, they also said that, okay, there's a tension with IceCube. Something what they've seen would be expected in 17 years of observation, which means that what they have seen can be explained as an upward fluctuation at the level of 2.2 sigma. This 2.2 sigma is in the ballpark of what the theorists are claiming. So the message from this slide is like both theorists and experimentalists agree that there is a tension between IceCube and KM3NeT, and it's really surprising that IceCube has not seen any neutrino event at such high energy. So
Vedran, I just want to ask one question.
go ahead.
Yeah. So regarding the dark matter decay, and if the flux of the y-axis is bit like 3 sigma, then with the dark matter decay, we can satisfy the IceCube flux. I mean the no observation. At the same time, we can explain the KM3NeT signal.
Well, the dark matter decay would produce some neutrinos.
Yeah.
And yeah, that would essentially be a diffuse contribution because dark matter is everywhere. But in that sense, I would say that the explanation would be more similar to this situation here, where you have a tension. So I don't understand. I've seen a couple of papers which are explaining and constraining dark matter using the KM3NeT event. But I believe that with dark matter, you cannot explain the tension. Let me introduce my concept and how this tension can be alleviated in the next few slides, and then I'll refer to this again, and then we can discuss more. But I'm fairly confident that in vanilla settings, if you just think about dark matter, you cannot explain the tension unless you play a type of game which I played in this work that I'm about to present. So give me maybe 10 more minutes, and then I think it's going to become more clear why dark matter, for instance, doesn't work in vanilla settings. Okay. So yeah, let me just discuss also very quickly this slide here. So here, how to get the spectrum of neutrino events. You multiply the data taking time, and you have this convolution here between the effective area and the flux. So what is inside of the effective area? It has the cross section, it has all the efficiencies for the detection in ice or water, whether you're thinking about KM3NeT or IceCube, and also has the volume factors. So you put in the effective area everything that is not flux, and this flux here is the flux at Earth. So if we look at 220 PeV, and I'm sitting here, you see that the IceCube effective area is 20 times larger compared to KM3NeT, which means that the red factor here is 20 times larger for IceCube compared to the KM3NeT. So if I want to explain the tension, I somehow need to have the neutrino flux 20 times larger or so compared to the 20 times larger for KM3NeT compared to IceCube, because otherwise I cannot explain it. Well, okay, maybe I can, Sarif, just again talk about the dark matter. So for instance, if we have dark matter decaying into high energy neutrinos, let's say 440 PeV dark matter decaying to 2 220 PeV neutrinos, you would still have a comparable flux of neutrinos at both location of KM3NeT and IceCube. And the effective area would still be much larger for IceCube, which means that you would not be able to explain this tension. So in my case, what I will use actually are sterile neutrinos, which are partially converting into neutrinos inside of the Earth. So the strategy is that I assume that there are sources which are dominantly producing sterile neutrinos, and these sterile neutrinos will then oscillate to active neutrinos inside of the Earth. And now you can say, why should they oscillate more strongly when traveling toward the KM3NeT compared to IceCube? And that's also going to be discussed later when I talk about the models. But first, I just want to say something about these sterile neutrino sources. Because, yeah, this would definitely be something non-standard already, because I really require the sterile neutrino flux from the source to dominate at Earth compared to the active neutrino flux. If active neutrino flux dominates, then both flux would be similar for IceCube and KM3NeT. And then I didn't do much, right? I didn't manage to explain the tension because I still didn't manage to compensate for this factor of the effective area. And what kind of sources can produce sterile neutrinos? Well, first of all, there hasn't been any gamma ray and gravitational wave detection of in connection to this KM3NeT event, so that gives us some room for speculations. That source can be something completely hidden. So, for instance, I have dark sector stars here. It can also maybe come from some local dark matter clump, but that will need to be some very high over density and something like a single source, not something that would give a diffuse contribution. And that would be something like dark matter decaying to sterile neutrinos, not dark matter decaying to active neutrinos. What is also possible is that you have, if you think about supernova, what happens in the center of the supernova, you produce neutrinos with the energy of like 150 MeV. And now these neutrinos will rescatter, lose some energy, and then they will exit the star with the 1 order of magnitude smaller energy. The supernova neutrinos are being detected at around 10 MeV. But if you produce some BSM particle like sterile neutrino, which is more weakly interacting, and if it's just produced at the center, it will just stream out without further interactions. And therefore, you would have effectively downscattering of active neutrinos compared to sterile neutrinos. And therefore, you can have sterile neutrinos at higher energies compared to active neutrinos. That's one situation I can imagine when I make a connection to supernova. So that would be this case here with the dense outer layer around the source. So this is all I can say about the sources. We honestly didn't think that much about the sources. Our picture is we have a dominant sterile neutrino flux at the location of the Earth. And the work is based on the following. This is the paper I'm presenting, the work done together with my postdoc, Dibia. And actually, I have the same pictures on the next slide, maybe even in a nicer frame together with the Earth. So actually, this is the main slide of my talk. Later, I will talk about some models, but this is actually, it all boils down to this slide. So we have so we have the KM3NeT detector here in southern Italy. We have the IceCube at the South Pole, and the people from the KM3NeT collaboration have detected the direction of the incoming neutrino. I'm still talking about this 220 PeV neutrino. And you can see the mean value of that direction. It has some uncertainties, which I don't have here considering that I'm working with their nominal values. You see that this is a very flat line here. So this event comes very close to the horizon. And when you take that direction, you see that the neutrino has passed 147 kilometers of soil and water. First, it passes through roughly 100 kilometers of rock, and then extra 50 kilometers of water before reaching the KM3NeT. Now we take the same neutrinos arriving from the same location in the sky. But now instead of KM3NeT, you focus on IceCube, because IceCube is down there in the South Pole. These neutrinos will come with a different angle with respect to the horizon, and actually it will be 8 degrees with respect to the horizon. And now with that angle, you know the directionality for IceCube. And here it turns out that this neutrino will pass only roughly 14 kilometers, 15 kilometers of ice before reaching the detector. So what will allow me to explain the tension is actually the sterile neutrino conversion into active neutrinos here with respect to here. You see that here I have more distance to play with. There's this mismatch in propagation distance inside of the Earth, and bigger L, bigger oscillation probability. And what I'm converting again is sterile neutrino into active neutrino, because otherwise it doesn't work. If I start from the active neutrino, then I'm just in the standard picture and I cannot resolve the tension. Again, if this event was not reported to come very close to the horizon at the KM3NeT, let's say if you follow my cursor here, if the event was coming from above and passing just these 3-4 kilometers of water, then I would, in IceCube, it would be comparable distance, and I would not be able to explain this. That means also that I cannot work with the diffuse fluxes and a bunch of different sources at different location. I'm committed to only one particular direction and a neutrino source from which from this particular event came, and which allows me to consider these two distances, and notice here that the order of magnitude longer propagation length inside of the Earth before reaching the KM3NeT detector. So that was the main point, and now I basically have two models, so bear with me. This slide has a lot of formulas, but I don't have too many slides with the formulas. And I will also try to make it a bit shorter, because I see that I spend a lot of time so far, but that's fine. I want to spend actually more time on the first part of the talk, discussing the event and the general solution. But here I actually want to, introduce some models and some concrete framework where we can actually explain this tension. So by now we know that we need sterile neutrinos, and we know that KM3NeT collaboration has recorded muons, and muons come from the muon neutrino upscattering just through the W exchange. So I'm working in a two-flavor scenario with muon neutrino and sterile neutrino. And in this model one, we're using a matter-induced resonance, the Mikheyev-Smirnov-Wolfenstein resonance, which tells you that the neutrino matter potential is at a resonance equal to this combination here of mixing angles, neutrino mass square differences, and neutrino energy. And if you just take the standard model, you can compute the matter potential to be of the order of 10 to the minus 23 GeV. That's basically G Fermi times the electron number density times square root of 2. And from that number, you can compute the resonant oscillation length, which is very simply connected to the potential. And what also enters into that formula is the mixing angle between active and sterile neutrino. And here we take 10 to the minus 3. Which is okay from the lab, but it's not okay from the cosmology. So I will have a slide how to have such a large mixing angle in cosmology without overshooting the ineffective constraints. But for the moment, let's just work with this number, and you're getting here the oscillation length at resonance to be 10 to the 5 kilometers. And I'll come back to the previous slide where I told you that the propagation of neutrino from the surface to the KM3NeT is 150 kilometers. So my propagation length is much smaller than the resonant oscillation length, which means that I will not be, when I plug things into the oscillation formula, it's going to be very small number. I will not be able to oscillate strongly. So there are two ways how to go about that. If you look at this formula, you have V. So if how to make the resonant oscillation length smaller, well, increase V, if I increase the active neutrino matter potential, that's really hard because there are a lot of strong constraints. But on the other hand, what gives you more freedom is to increase the sterile neutrino matter potential, and that's what actually we did in this model here. We basically adopted the Pospelow's, so-called Pospelow's baryonic neutrino scenario, where you have spontaneously broken baryon number. And here you have the respective gauge boson talking to sterile neutrinos and also to quarks. So you can use that and write a 4 Fermi operator where you connect on one side the sterile neutrinos, and on the other side you have now protons and neutrons, because if you couple to quarks with this charge, baryonic charge 1/3, you also couple to protons and neutrons. Given this effective Lagrangian, I can shoot for the sterile neutrino potential. For those of you who did this kind of calculation before, you may remember that this boils down to the expectation value of these two currents, which are just the result is the number density of protons and neutrons. And then you get something like number density of scatterers multiplying the GB in this case. That would be the strong, this strength of the force. That would be analog of G Fermi for this baryonic force. In the standard model, we have potential equal G Fermi times the number density times some factor, and now you basically have the similar result here. But I have both protons and neutrons contributing because they both interact through this baryonic force. So at this point, after I computed the potential, I can just plug that into the Hamiltonian. I have the vacuum term. And again, remember, we are in two flavor pictures, so these are all 2 times 2 matrices. And from the potential perspective, matter potential, I have the contribution for the standard model muon. This term here, VNC, is just the neutral current scattering of muons with electrons, protons, and nucleons. And Vs, the sterile neutrino matter potential, is just what we computed in the framework of this model on the previous slide. I'm not going to be working with this Vs. I like to work with G Fermi times epsilon SS, which will tell me how much stronger than G Fermi this interaction actually is. And what we are going to be playing with is something that is even 100 to a couple of hundred more stronger than G Fermi. And I can already tell you that from the neutrino phenomenology perspective, we checked the whole, atmospheric, solar, reactor neutrinos. None of those are spoiled by these new interactions, even of this kind of magnitude. So that phenomenology is just not altered. But I will also have one slide to discuss in general constraints, because some of you may definitely be concerned about the fact of using such a strong new interaction.
I have a question.
Yeah.
Is it okay with the collider experiments as well?
Maybe you can give me a slide and then I'll just discuss. Catch me up there if the answer will not be satisfactory. I have a bunch of constraints on this model listed in like a slide or two.
So you're assuming 100 times or 1,000 times stronger interaction with the sterile neutrinos with the standard model protons and neutrons.
The interaction strength is 100 times G Fermi. Yes, this interaction of this new U1 baryon number. This order of magnitude has already been employed, order 100 times in this paper by Pospelov and several other papers. I will show you the current state of the art of the literature for the constraints on this U1 baryon number. Just give me one slide or two. I would like to first finish the phenomenology, and then I'm going to be honest about the constraints.
Okay, please go on.
So now that I fixed the interaction strength, and we have the energy of neutrino of 220 PeV, we can also use that formula for the previously described formula for the resonance to get the actual mass of sterile neutrino, for which I would basically have the resonance, and that actually points to the KV sterile neutrino. And here on the plots on this slide here, you basically have the resonant enhancement of the mixing angle in rock, water, or ice for both KM3NeT and IceCube, and the respective change for the mass square differences. But actually, in reality, we haven't used that. This is in constant matter density. And since, if you remember, for KM3NeT, you first pass through some rock and then water, we just solved the Schrodinger equation. We just, solved the Schrodinger equation driven by this Hamiltonian in order to get the realistic values of sterile neutrino and the Moore neutrino fraction at KM3NeT. And these are the results. So here, let's look at the larger plot. Y-axis is the sterile neutrino mass. X-axis is this new interaction, and now it has a minus. Minus, nothing smart about this minus. We want to achieve the resonance in the neutrino sector. If we wanted to do the resonance in the anti-neutrino sector, then we would flip this sign. So this is just a sign coming from there. So you can overall see that the oscillation probability for KM3NeT, and by the way, these are all evaluated for KM3NeT at 150 kilometers because that's our propagation length, and at roughly 15 kilometers, which was the distance for IceCube in that previous plot. And you can see that the oscillation probability for KM3NeT is at least an order of magnitude larger. So if we look at this overlapping region, you see that there's 10 to the minus 1 for KM3NeT, 10 to the minus 3 for IceCube. And for one particular benchmark point, maybe look at this plot here on the upper left. The resonance is actually achieved here at the value of epsilon around 150 for this parameter point. And you can see that the oscillation probability of KM3NeT is more than an order of magnitude larger than IceCube. So what does this mean? I have much larger conversion from sterile neutrino to Moore neutrino en route to the KM3NeT, which means that I'm going to generate much more Moore neutrinos in Earth when traveling toward the KM3NeT. And now I'm coming back to this formula here. If you remember, I had a problem that IceCube effective area is 20 times larger. Now I managed to actually get the active neutrino flux to be, well, 20 times larger for KM3NeT, which exactly compensates for the problem in the effective area. Yeah, that was the model one. And here I would like to discuss the constraints. So now I'm actually coming to your question. This U1 barrier number model has been discussed in the literature, not as much as something like U1B minus L, that would be this one here, which features all these constraints. This is an old paper from Harnik, Kopp, and Machado. And what they're basically saying in that paper is like, okay, these are all the constraints. You have all the check marks for B minus L model. But what happens for U1B model? That's the one I'm talking about. You see many X's and very few check marks, meaning that many of the constraints will not be applicable for U1B. So for instance, if you think about the fixed target experiment, that would be like a beam dump. You produce your Z prime at the beam dump experiment. A beam dump, this A prime that is produced then is going to decay. If you have only U1 barrier number coupling, you don't basically have an option to decay if your Z prime is lighter than the pion mass. And the only available channel may be, E plus E minus, which would work for B minus L case, but not for U1 barrier number. Similar things for light shine through walls experiments and several others. So in general, most of the limits from this plot would disappear. However, there are still strong constraints, and this is a more recent plot. Let's look at this one. This is 2017 from Pospelov, Dror, Lassenby. Here, they basically have a set of constraints from the meson and K-on and Z decays, and also this anomalon bound, which is important. Notice that U1B is not anomaly free, so we need to put some heavy fermion in the model. And this heavy fermion mass would be some Yukawa coupling times the VEV of the Higgs, which is breaking this symmetry. And we also know that the mass of this gauge boson corresponding to U1B is a gauge coupling times the same VEV. So given that we have constraints on the searches for hidden fermions, we can basically use that information as to set a limit on G. So requirement of around 100 for the epsilon SS would be achieved in this region. In this region, order 100 enhancement with respect to G Fermi is achieved. Things are much more strict here for the lower masses. But I should also point out that if you manage to arrange that there is no kinetic mixing between this dark photon corresponding to U1b and the standard model photon, then also most of these constraints from this paper would actually be alleviated. So in that sense, even if that is not the case, there are parameters regions here where you can achieve such a strong interaction. Yeah, so this is all I can say about the constraints on the model. So maybe now you can reply if that was satisfactory, or do you have further questions on that?
What about the monophoton search at the LHC, for instance? PP produce the sterile neutrinos and generate another photon? Because you are having pretty strong interaction with the Z prime and sterile neutrinos.
Right.
So I guess that can be one dangerous signal.
That's maybe something to, yeah. Honestly, that one, yeah. PP go to US and then you just radiate a photon. That's in principle something that should be there, and the constraints should be there. There should also be some mass dependence on this limit. So
yeah, that's right. Yeah.
I'll try to look into this, but I don't have an answer right now.
Okay. Yeah.
I suspect that folks from this work here have thought about this, and I should actually look if some of those constraints we're talking about are actually in this gray region here. But yeah, that's a good good point, because the interaction is indeed quite strong.
Yeah, please go on. Thanks.
One other thing that, and actually I see that my time is really running out, so maybe this slide is not that important. At some point I said that the interaction between, mixing between active and sterile neutrino needs to be very large. And here I just want to discuss very quickly that there's been a lot of work how to alleviate that from the cosmology. So I'll maybe just choose one of these bullet points and say that what has been studied is like interaction of sterile neutrino with ultralight scalar particle, which can be dark matter. And then if you make sterile neutrino supermassive in the early universe with a mass, comparable or larger than the temperature, then this sterile neutrino would not be produced in the early universe and would not cause a problem from the N effective. Otherwise, with very large mixing, your N effective would be 4, and that would be ruled out. So my explanation here also requires this kind of additional alleviation of the problem with the cosmology, which means a further extension of the model. So yeah, in the previous this slide here, I discussed and showed how this works for KM3NeT versus IceCube. Here I discussed 2 limits, and I also have just very quickly model 2.
Yeah, so it's not a strict 1 hour time limit, so don't feel rushed. Take your time.
Okay. Well, I think you said 50 minutes plus 10. Okay, yeah, there's still discussion being, yeah, I think I'll still be able to wrap up relatively quickly. Yeah, and I'm kind of also running out of slides, as you can see. The model 2 is something that somewhat complementary. So we also thought about can we not use the resonance? And actually, this model is more healthy from the mixing point of view, because I don't require large mixing between sterile and active neutrinos. And also, I'm not working here with U1 barrier number. So here we start phenomenologically from the following Hamiltonian, the same term as for the model 1. This is the vacuum term. And here I got, again, the contribution for the muon neutrino, neutral current. And as you can see now, there's no this 2-2 element for steriles, but we just introduced this off-diagonal term, which is parameterized as epsilon mu s. That is a new non-sterile interaction strength. Here it's multiplying VCC just to show how large this basically epsilon parameters how large this is compared to the standard model matter potential. How can this term arise? The answer is you would need to have a non-sterile interaction term of this form. The off-diagonal non-sterile interaction terms are quite well studied in the literature, but there you usually have two active neutrinos connected into this 6 Fermi operator with electrons, protons, or neutrons. Here, notice the new thing is that you have sterile neutrino talking to muon neutrino. I don't know how to model build this, but for instance, Babu got interested and he started thinking about the UV completions for that. And I have only looked at this purely phenomenologically. And interestingly, we have even not found any previous phenomenological studies for this kind of operators. So we had to go from scratch and again see if all the low energy phenomenology is okay if you're playing with this operator. But before I discuss that, I will just say that, with these new matter terms, you can have your mixing angle and mass square difference expressed with these new matter terms. And you can go back to the oscillation probability and just express the formulas. Here is a famous formula for two-flavor oscillations in two-flavor scenarios, where I'm just replacing the standard with the this effective mixing angle and the mass square difference. And upon plugging all the numbers, you find again that KM3NeT probability for sterile to muon neutrino conversion is much larger than IceCube. You can see again here factor of L, and remember that L is much larger for KM3NeT than IceCube because in-earth propagation for this particular event happens to be order of magnitude longer. And this is all this is based on. You see here values roughly 2 orders of magnitude larger for KM3NeT. And this holds for any value of epsilon mu s, though I prefer larger values because for larger values, the oscillation probability is larger, which means that my initial sterile neutrino flux at Earth should be smaller. The requirement is weaker than, if this conversion probability is very small. We looked again at the whole oscillation, low energy oscillation compared to the low energy oscillation data and verified that even for values up to 10, we don't run into trouble regarding the predictions of the atmospheric, solar, and reactor neutrino fluxes. So we don't modify those and introduce some, I don't know, some extra kinks or some new anomalies at the low energies, even with such large values of epsilon. So again, just to summarize and connect also to the model 1, in this case, again, the difference in the propagation length between the KM3NeT and the IceCube is order of magnitude larger in favor of KM3NeT, and that leads to this difference in oscillation probability, implying a stronger production of muon neutrinos, and bigger neutrino flux at KM3NeT is exactly what compensates for larger effective area at IceCube. I should point out that after our work, there are a couple of interesting works which also employed the strategy I talked about, namely the stuff from this slide, and that the propagation length is much larger for KM3NeT. So, but the work from these two groups is somewhat complementary. So we did the oscillations, we produced active neutrinos from oscillations. These two groups actually use scattering, which is also, of course, legit. If you have more matter, you can oscillate more. But if you have more matter in front of you, you can also scatter. You have also more bigger likelihood that you're going to scatter some dark matter particle and produce active neutrino or muon. If there's 150 kilometers of rock in front of you compared to like 10 kilometers in the IceCube. So this plots here the sequence of Feynman diagrams. It's coming from this paper by Bhupal et al., which has production at blazars. Then you have this Chi1 that shows up at Earth, and in Earth it upscatters to Chi2, and then this Chi2 decays into more neutrinos. And this scattering is going to be much more is going to give you bigger flux of Chi2 and route to Earth because you have more matter where you can perform the scattering. So yeah, so I just wanted to point out that there's more works, and all of our works are based on the fact that there's a mismatch between the propagation length and route to IceCube, between the KM3NeT and IceCube. So coming back to the original question from Sarif in connection to dark matter, I would say that the dark matter can definitely explain this tension, but I would say that that should be dark matter which produces sterile neutrinos, and then you have these sterile neutrinos oscillating, or some game that was played in this paper with this additional upscattering. If you just have dark matter producing active neutrinos, then that would just be as effectively equal as a regular neutrino flux, in a sense that you would not resolve the anomaly. But that kind of work is still valuable. For instance, if you take 220 PeV neutrino at a face value and constrain like the dark matter mass and lifetime parameter space. And I've seen also papers doing that. But those papers are constraining neutrinos in neutrino properties, dark matter properties using that neutrinos, whereas in my work and these two papers that I'm showing here, our priority is to resolve the tension between the two experiments. So yeah, let me wrap up. I'm on the last slide here. The KM3NeT collaboration observed the highest ever neutrino reported. It's above 100 PeV. IceCube has not seen that, and it's a 3 sigma tension. The strategy we employed in our work is basically compensate the effective areas with the neutrino fluxes, and how to make neutrino fluxes larger than at around KM3NeT. Have the fluxes at Earth, at the surface of the Earth, being mostly sterile neutrinos, and then leverage this difference in the propagation distance between KM3NeT and IceCube, 150 versus 15 kilometers, in order to have a much bigger likelihood to convert sterile neutrinos to active neutrinos at KM3NeT, and this is exactly what which generates larger neutrino flux, active neutrino flux at KM3NeT, and explains resolves the anomaly. And with that, I'm done. So thanks.
Thank you for the nice talk. Are there any further questions?
Yeah, actually, I have a question about the source. Right. So you mentioned one particular source here, and also you mentioned the blazar as the source of the dark matters, right? On the other hand, if you really take the direction of the signal, that's almost opposite of the galactic center, and no supernova blazar are identified from that direction. Could you comment on this?
Right, indeed. There has been no photon or gravitational wave in association to this neutrino. So yeah, they haven't found the source, which is great for my work, because you see that I'm trying to sell you here a non-standard source. There's definitely some non-standard stuff going on here, because I require, for my explanation, I need to have dominance of sterile neutrino fluxes. And here I could have only illustrated qualitatively, not quantitatively.
Yeah, your point is very clear. Very nice. Yeah, I'm just
what I can also maybe briefly say that in this paper here, they were looking at the blazar production. So,
but no blazar is identified.
But no blazar is identified. That's true. So, there is still, well, yeah, that's maybe a bit tricky. Yeah, I'm not the author of this work, but what I can at least say in their defense is that here they're basically they actually identified the particular production mechanism at the source. So this is interesting because from the perspective that you can produce BSM directly in the source, and they have a concrete Feynman diagram. The fact that they need a blazar and that blazar has not been identified, that's I guess that's more appropriate question to people who are doing the IceCube catalogs and these coincidences between photons and neutrinos. It probably doesn't exclude the blazar overall, the fact that they haven't found the blazar so far. Yeah, this thing with the source will remain speculative for the time being. But maybe even in the near future we get more events from the same direction, and then the picture might become more clear on what's actually going on.
Agree. Yeah. Thanks.
I just want to say that yeah, with the dark matter lifetime and dark matter mass, we cannot explain the center of the KM3NeT signal, but we can explain the 3 sigma flux of the signal. And that's what basically people do with the dark matter decay.
Sarif, but you also have to take care of the direction, right? If dark matter is the source, the conventional dark matter is the source, then you're likely to have more signals from the galactic center, which is really difficult to explain the data because the direction is basically opposite of the galactic center.
Yeah, exactly. But we can have the dark matter distribution, and along the direction also we can have some dark matter distribution, and from that we can decay. But we can also have the extragalactic as well.
Right. But yeah, just again to discuss this, that's interesting. And I would say that there are 2 different perspectives I've seen in the literature. Maybe I missed it, but Sarif, it appears that maybe if you have a paper on this, just let me know. Maybe I missed it, but you seem to speak in that way. So I would say that our work and the works from these 2 groups focused on saying like why IceCube has not seen the event. What you're talking about, the dark matter lifetime and the mass, is another legit but different perspective, right? Your perspective is like, okay, I have a neutrino event at KM3NeT. What can I do with that? And then you set, some of the leading constraints on the dark matter decay. And in that story, the IceCube is not discussed or not relevant, right? So yeah, these are, I think, and I've seen these 2 different types of works in the literature so far in connection to this event, and I guess they can even be merged in some sense if, for instance, you have dark matter decaying to something dark. It could be that I need to check this Bhupal's paper a bit better, but maybe Chi1 or Chi2 here is dark matter, so maybe they have both features somewhat implemented.
Yeah, basically, yeah. In our study, we basically showed that the flux is below the IceCube. But in our case, we have also checked that we can easily implement your scenario. It can directly decay to the sterile neutrino.
Okay.
And then it can actually have the same kind of effect as you have.
Right, but okay, if you implement in my scenario, then it's then you would, I guess, have a multi-parameter space. It would not be only dark matter, but yeah, I agree that in principle it can be implemented. It's just that if you have a dark matter decay, and let's go back quickly on actually, where did I want to go? Maybe no, actually, I wanted to show this one again. So here, the directionality really matters. To explain the tension in the context of dark matter, what I can imagine is that what would be much more favorable if not using the normal dark matter distribution, but to have some dark matter clump in this particular direction that would give you a dominance. So people have constrained, you can have some local, very strong overdensities of dark matter. If you have something like that, instead of like a completely, diffuse extragalactic contribution, that would definitely help because, if I have one direction, then I can play the game between this mismatch in distances. If I allow for all possible directions, then things will average out and I will have no advantage of KM3NeT over IceCube in this case. So that's just a small caveat about that. But in principle, I agree that dark matter is a legit way how to explain these things.
That is also an interesting aspect. Document example.
All right. Great. Well, there's no more questions. Let's thank the speaker again.
Thank you very much.
Yeah,
Thanks a
thank
lot.
you.
Thank
Yeah.
you.
Vedran?
It was a
Thank
nice
you.
talk, yeah.
Cheers,
Vedran,
bye.
could you pass my regards to Kaladi Babu?
I will.